Okay, so good morning. This is our formally the first lecture for the course ME 514. Already you know the title for the course is Fundamentals of Multiphase Flow. And in this very first lecture, we will simply go through the introduction to the course. Okay, so before that, let me give you some important details. So instructor, already you know me about the teaching assistants for this course. There will be two teaching assistants. One will be Mayank, who is a Masters of Science student in mechanical engineering, and his email ID and contact details are given here. Similarly, another student will be a PhD student, and his email ID and contact details are also given here. So both of them will be teaching assistants for this particular course. Okay. Then let's quickly go through the syllabus of the course. So in this particular course, we have LTP scheme. All of you know lecture, tutorial, and practical. So we will be having 3 lectures, no tutorial, and there is no practical. Okay, so formally there is no tutorial and practical, but as I will be actually going through some of the computational techniques about the multi-phase flow. So whenever required, whenever we will be doing some example problems for setting up multi-phase flow problems using some computational solvers, then some of the lecture sessions we will try to convert into practical sessions. Okay, and overall scheme, you can see the very first module will be introduction and flow designs, and mostly we will be spending something around 6 lectures on this module for covering the introduction. This module is important because whenever we start studying any of the course, before that we should know about different nomenclatures which are relevant for that particular course. Okay, for example, when we talk about thermodynamics, then the properties, thermodynamic properties of the fluids are very, very important, and if we don't know about the properties, then we cannot proceed with the analysis of the thermodynamic systems. Likewise, when you talk about the fluid mechanics, then along with the thermodynamic properties of the fluids, there are certain flow properties. For example, velocity, okay, displacement of fluid particle, etc., streamline, streak line, etc. So these are the things which are again the nomenclature related to that particular course. If that nomenclature is not clear to us, we cannot further understand the details of the fluid flow. Okay, so likewise, whenever we will be talking about the multi-phase flow systems, because it is not uh, simple as that of the single fluid systems, here we will be having actually presence of 2 or more than 2 fluids at a same time within the system which we are considering for study. Okay, so because of this, there will be some specific nomenclatures which will be very specific to multi-phase flows only. We have to get aware to this nomenclature, then only we will be able to, after that only we can analyze the multi-phase flow systems. Okay, then second module will be modeling techniques for multi-phase flow. So typically these modeling techniques which are listed over here, these are the analytical modeling techniques for analyzing different multi-phase flow problems. What we will do over here, we will slightly try to change the structure of the course. So instead of discussing this module immediately after the introduction, I will try to discuss the experimental techniques immediately after the introduction and flow designs. Okay, because if we see nowadays there are significant advancements in the experimental techniques as well as the computational techniques for analyzing different multi-phase flow problems. Of course, these analytical techniques have their own importance, but still people more often nowadays are using experimental and computational techniques for analyzing complex multi-phase flow problems, because the applicability of analytical systems is actually limited. So analytical models can be applied with significant number of assumptions, and that too very simplified set of problems. If we have to tackle very complex situations, then using pure analytical models may not suffice. So that is the reason structure I will be slightly modifying, and first we will discuss the experimental techniques. After that, we will try to discuss different computational techniques which are used for modeling the multi-phase flow, and then we will be actually entering into this analytical techniques near the end of the course. And after that, if time permits, then we have provision for some special topics in multi-phase flow depending upon the availability of the time. In special topics, many things are listed. For example, granular flows, slurry transport, Lattice-Boltzmann method, and microfluidics, multi-phase flow in microchannels. Of course, these are all very detailed topics. We will not be able to touch all these topics in detail. Out of all these, I will try to give some idea about phase change heat transfer in detail. Okay. So, in special topics specifically, we will be talking about phase change heat transfer in detail. So, this is about the syllabus for the course. And then, of course, there will be certain books which will be followed. So, typically, uh, three books will be majorly referred, and out of which fundamentals of multi-phase flow, C.E. Brennan, this will be used for the first module, and then for special topics, two-phase flow, boiling and condensation, S. Mostafa Ghassian will be used, and for computational techniques, direct numerical simulations of gas-liquid multi-phase flows by Trigvason, Scardovelli and Stephen Jeleski will be used, and as and when needed for different experimental techniques, etc., or some special topics, these other reference books can also be used. But majorly we will be actually referring to these three books. Of course, all the three books complete we will not be doing. For example, as I already told you, for initial module I will be referring to first one, then for computational I will be referring to this one, and particularly for experimental techniques, majorly it will be from this book, and then for phase change we can actually refer to this particular book. So depending upon the topic, we will be using different books. Okay. Some of these books you can find the copies in the library as well, and in case you are finding it difficulty, then you can obtain these books from me as well. Okay. Now, course plan. Of course, if we have to do this course, then what is the prerequisite for the course? So, engineering thermodynamics and fluid mechanics and heat transfer. These three courses you should have basic understanding of these three courses when you are actually coming for the classes of multi-phase flow. Okay. And attendance policy as per institute, it is 80%. And evaluation scheme, so there will be two quizzes. One will be before midsem and other will be after midsem, and each quiz will be of 10 marks, and I'll try to keep these as surprise quizzes, so you should be prepared for quiz. Okay, in case of extreme circumstance, if you are missing the quiz, then we can have some arrangement, but that is based on some genuine reason. Okay, and mid-semester exam will be of 30 marks, final exam will be of 40 marks, and along with that there can be one research paper presentation. So somewhere near the mid-semester exam, after the mid-semester exam, you can actually decide some research paper, because by the time we will be having sufficient idea about the multi-phase fundamentals of multi-phase flow. So you can choose any research topic related to multi-phase flow, and you can download a research paper related to that, and then that research paper you have to make a brief presentation, and based on that presentation you will be given actually 10 marks. Okay. So if you have to start multi-phase flow, so let me tell you, because you can see that all of you have studied fluid mechanics. So whenever we analyze the fluid flow problems, there also the amount of complexity we solve, that you have already seen in your basic fluid mechanics course. For example, when you study flow between the two parallel plates, Poiseuille flow, plane Poiseuille flow. When you study flow through a pipe, Hagen-Poiseuille flow. So you know that we have some governing equations, for example, continuity equation, momentum equation. Okay, we try to simplify these equations for the given flow situation, and once we have simplified version of the continuity and momentum equations, then these simplified equations are subjected to the set of boundary conditions which are applicable for the given problem, and then analytically we try to find the solution. Okay, but from our understanding of fluid mechanics, we know that this analytical solution of the continuity and momentum equations for fluid flow is available for very simplified set of problems. Okay, it is not available for all the kind of complex flow situations, because whenever we are solving these differential equations for the given flow problem, based on certain assumptions, majority of the mathematical terms actually we are removing from the equation, and only the terms which are having significant contribution, these terms actually we are considering for flow problems. So there we make thousands of assumptions. For example, even in flow through a pipe, we say that flow is parallelly aligned along the wall of the pipe. Okay, so there is no component of velocity in normal direction. Okay, so all these are nothing but the simplified assumption. But whenever we will be studying the multiple fluids simultaneously in a system, then situation will be becoming more complex. So because of which multi-phase solution of multi-phase flow problems is more complex, and that is the reason that majority of the complex multi-phase flow problems are tackled either using experiments or CFD, computational techniques. Okay, so analytical solutions becomes quite challenging. So Professor Barry Ejopardi was stalwart in the field of multi-phase flow, who has contributed significantly in experimental techniques of multi-phase flow, and this is one of his statement where he mentions that multi-phase flow is a bigger problem for any one person to solve. We have to do what hyenas do, attack the problem as a pack from all sides, and sharing data is the key. Okay, so of course, whenever I will be now talking about the occurrences and applications of multi-phase flows, you will be finding that it is hard to find any industrial or natural scenario where multi-phase flow is not present. So an individual person cannot solve all the problems. So different people can actually try to understand different facets of the multi-phase flow, and of course then once the data is available in terms of open literature, then that can be disseminated to the entire community. So let's now understand what is multi-phase flow. Okay. So can you give me some idea what is multi-phase flow? And a special version of multi-phase flow is something which is called as two-phase flow. So if I have, first condition, if I have a system in which more than two fluids slash phases are present, then we will be calling it as multi-phase flow. If we have two different phases or fluids present in the system, then we call it as two-phase flow. Okay. So do you understand the difference between phases and fluids? Two phases can be, say, I have my pressure cooker. Okay. So inside this pressure cooker, what I will be having? Inside this pressure cooker, I will be having water at the bottom, and at the top portion, I will be having steam, or I can say water vapor. Okay. So now substance is same. Here also I am having H2O molecule, here also I am having H2O molecule. But at the bottom it is in the liquid phase, at the top it is in the vapor phase. Okay. So I can have a situation where two different phases of a same substance are simultaneously existing, or more than two phases are simultaneously existing. Second situation can be, I have a container. In this container, at the bottom I have water, and at the top I have some oil. Okay. So what we have in this situation? In this situation, we have two different fluids. So this type of system will be kind of a multi-fluid, or I can say multi-components. So here if you see, both the fluids are in the same phase. Oil also in the liquid state phase, and water also in the liquid state. Okay. But only difference is these are as two different components. Is this point clear? So this will also be coming under the category of multiphase. But one small thing we have to consider over here, if I say that this oil and water, these two are lying stationary. Okay. So if these two are lying stationary, what I will be finding? I will be finding that here I am having water phase, here I am having oil phase. And somewhere over here, there is some border, okay, across which my component is actually changing. So this particular border surface is something which is called as interface. Okay, so this particular boundary which is segregating the two components, two fluids, or even if you talk about steam and water. So in steam and water also, these forms an interface, because steam is not miscible in water. Okay, so ultimately steam molecules will stay at the top and liquid molecules will stay at the bottom, and in between also we will be having some interfacial boundary. Okay, so here also we have interface. So the boundary between the two phases or between two fluids is something in a multi-component system, is something which is known as interface. If my interface is stationary, okay, and it is not changing with space and time. So if you have, say, container stationary, if you see at time t1, it will be at this location. If you see at other time t2, say, which is t1 plus 15 minutes, then also it will be at the same position. So here I can say that it is a multi-component system, but I cannot call it as multi-phase flow, because when multiple phases will be flowing together, the interface boundary will not be remaining stagnant, it will be changing with time. Okay. So for multi-phase flow to happen, the second mandatory condition is that interface should evolve with space and time. So here also same will be applicable. if interface is not changing with space and time, then we cannot call it as flow. So once interface is changing with space and time, then only we will be able to call it as flow. Okay, is this point clear? So these are the mandatory conditions for multi-phase flow. Now, multi-phase flow can be of different types. Let's understand what different types we can have. So, first we are starting with the two-phase flow. So, first statement already I told you that either there should be two phases of a substance or two different components. And second point is there should be breaking and making of time and space variant interfaces. So interface should evolve with space and time. Now there can be different types of this type of fluid behaviors. So one of the photograph is given over here. This photograph is of a vertical tube. In this vertical tube, water is filled, okay, and in this water a kerosene medium is actually introduced. So this is nothing but a two component system. Liquid is one another fluid, kerosene is some different fluid. Okay, now this kerosene is introduced in such a way so that what will be happening if you have a tube, and in this tube, if from the bottom you introduce kerosene, what will happen? Density of the kerosene is less in comparison to density of water. So if tube is aligned in the direction of gravity, this kerosene will try to rise in upward direction. Okay, so there can be different possibilities. In this scenario, we are considering that the volume of kerosene which is rising in upward direction is significant. If volume of kerosene is significant, then it takes this particular shape. Okay, and in this shape, it is actually rising in upward direction. Okay, so here, what you can see? You can see that in between the kerosene and water, you can clearly demarcate boundary. Okay, you can clearly demarcate boundary. So here interface is actually clearly visible to us. And of course, at the wake of the bubble, there are again small bubbles which are observed at its wake. But if we don't focus these small bubbles at the moment, if majorly we focus on this large chunk of the kerosene, I can make a clear separation in between this kerosene and the water. Okay, so this type of flow is typically called as well separated flow. So you can have a schematic representation where you can show with this boundary that you have different phase, and outside this boundary you have different phase. Okay, so once you can clearly segregate the boundary between the two components or two phases, that type of flow situation will be called as well separated flow. Is this point clear? Second situation could be that in the same tube, once we are injecting the kerosene, instead of forming a bigger chunk, this kerosene is dispersed in the form of small volumes within the complete volume of the water. Okay, so here you can see the situation. These blue colored dots are nothing but, these blue colored circles are kerosene volumes, and these are significantly distributed within the water. In this scenario, it is extremely hard to define a clear boundary between the two phases. Okay, this type of multi-phase flow situation is called as well dispersed flow. Is this one clear? So for example, if you take a bottle, in the bottle, if you half filled it with water, half you filled with oil, and then you try to shake it. Okay, so what you will be finding, that oil and water are significantly mixed with each other. So this type of situation is actually called as well dispersed flow. When you allow this bottle to settle for long duration, after that again there will be separation because of the gravitational state. Is this point clear? Now, so we have seen that these flows can be categorized into broadly into two categories. One can be well separated flow, other can be well dispersed. Okay. Then comes important point. Whenever we talk about the multi-phase flows or two-phase flows, here you can see a video. Here you can see a video. So what is this? This is nothing but co-flow of air and water in a tube. Okay, so there is a vertical tube, and from the bottom we are inserting both water and air together. Once we are inserting water and air together, you can find that water is becoming a surrounding medium, and in this water a big chunk of air is coming, and behind this chunk of air there are large number of small bubbles, and after some time another chunk of air is coming, and again at the wake of this chunk there is formation of large number of small bubbles. Okay, so behind this every chunk of air, so this is a big chunk of air, behind this every chunk of air, whatever these small bubbles are there, these small bubbles are typically called as satellite bubbles. Okay, and this large chunk of air is something which is typically called as Taylor bubble. Okay, so this is called as Taylor bubble, and these are called as satellite bubbles. Now, it is interesting to note, when single phase flow happens through a pipe, okay, then to characterize that flow, whether flow is laminar or flow is turbulent, what we do? We calculate Reynolds number, and as per the definition of the Reynolds number, we have rho Vd by mu, where we consider that internal diameter of the tube is actually my characteristic length. Okay. However, in the multi-phase flow situation, what you can observe is, there I have a big chunk of the bubble, which is a slug bubble, which is a Taylor bubble, and then this is my, say, internal diameter, then this is the length scale of the Taylor bubble dt. Apart from that, I have large number of small bubbles of different sizes. Okay, so size of each of these bubble is completely different. So it means that here there is not existence of a single length scale for this situation. Okay, so there are variety of length scales available. One is diameter of this particular bubble, other could be diameter of pipe, third could be individual diameter of these small bubbles. Okay, so which one to use while we are calculating the non-dimensional numbers. That is extremely difficult to decide from this complex situation. Okay, so that's why these type of multi-phase flow problems are of multi-scale nature. Okay, multiple length scales are actually existing over here. Moreover, if you have a larger size bubble which is rising in the tube, that will be having different velocity. So uh, moving from one end of the tube to other end of the tube, it will be taking say t1 amount of time. If you have very small size bubble, that will be having different amount of buoyancy force, so it will be taking some different amount of time. So depending upon the length scale, whatever the time this bubble will be spending in particular system, that will also be different. So here in multi-phase flow system, there is existence of different length as well as the time scales. Is this point clear? So length and time scales are not same. And this is the reason this problem can be called as multi-physics problem. Why multi-physics problem? Because whatever the water is flowing, that is having some different dynamics. This larger bubble is having some different dynamics, smaller bubble is having some different dynamics. So each of the component is actually behaving differently. So that is the reason that this problem can also be called as a multi-physics. Yes. These are also satellite bubbles. So if you have a larger bubble and in its wake, whatever the small number of bubbles are forming or dissociating from its wake, these are typically called as satellite bubbles. This is the inherent nature of the flow. So this depends upon different situations. For example, the way you have designed your inlet. Okay, so in your inlet there can be different arrangements. For example, you can have this type of inlet. Okay, so here from this you can pass here, from this annular space you can pass water. Other arrangement can be from center you are passing water, from sides you are passing air. Third arrangement can be you have some porous structure over here. Through that porous structure you are simultaneously passing air and water. So depending upon these different configurations, different type of flow structures or phase associations can exist. Okay, how to categorize it, how we govern this, that I will show in the subsequent discussion. Moreover, each of these type have their own benefits. If you are talking about chemical reactions between the two components, if you are talking about heat and mass transfer between two components, then dissociation of larger volume into smaller volume is actually a good requirement, because then interfacial area will be increasing. More is the interfacial area, more will be the heat and mass transfer. Okay, faster will be the reaction between the two reacting species. Okay, so it all depends upon the configuration of the system, the size of the channels, the way we are allowing inlet and outlet. It depends upon properties of the participating mediums. It depends upon their flow properties, velocity and flow rates, etc. Okay, so we will be categorizing these different flow regimes to demarcate between the different type of occurrences of the two fluids. Now, one important point to note: I told you that if I have, say, liquid 1 and liquid 2 then the boundary between these two is something which is called as interface. Okay, or likewise, if I have say vapor and liquid, then also the primary condition is two components or two phases which we are considering, these should be of immiscible nature. If these are miscible to each other, then they will form a homogeneous fluid and boundary between these two will not be existing. Okay. So in a scenario of immiscible two liquids and vapor and liquid, we will be having some interface. Now one important point to note. Can you tell me, will this interface be a two-dimensional surface or a three-dimensional volume?
Three-dimensional.
Why?
Because it's a fluid. The interface should be across the three dimensions, right?
See, for example, if you have a container, you have water at the bottom, oil at the top. So in between water and oil, interface will be looking like a plane, 2D plane.
But sir, let's say we are talking about cylindrical.
Yes,
Between city of
cylindrical. Let's say this is cylinder. Let's say this is my air and outside is liquid. What is this boundary?
but in the last case where we have kerosene and water, then in that it will be city of
Here, how?
it is like this.
Yes, it is like something like this, and then extending as a hemisphere at the top. So when I am talking about interface only, I am not talking about bulk medium. You have to understand this. See, this is one bulk medium 1, this is bulk of medium 2. If I remove bulk medium 1 and remove bulk medium 2, what I will be getting? I will be getting a plane, a 2D surface. Is it clear? So, if I look from macroscopic viewpoint, so if I look from macroscopic viewpoint, what I will be finding, that interface is nothing but a 2D surface. Is this one clear? Interface is nothing but a 2D surface. Okay. It means that say somewhere over here I have interface, and my system is say air and water. Okay, so after the interface, here I am having air, here I am having water. So if I look from macroscopic viewpoint, it tells me, if I am say plotting over here density, then up to this point the value of density will be equal to density of water. At this point I will be having a sharp discontinuity, and then here I will be having density equal to density of. So from macroscopic viewpoint, if we are considering interface to be a 2D boundary, then I will be having across the interface sharp discontinuity in fluid properties. Is this point clear? So we will be having sharp discontinuity in fluid properties. On the other hand, if you look from microscopic point of view, what will be happening?
Slightly.
In case of microscopic viewpoint, if you enlarge this interfacial portion, if you zoom in, you will be finding that in liquid side, the water molecules are closely packed to each other. So all these are nothing but say water molecules. Okay, and then here I will be having loosely packed molecules, which will be air molecules, and there will be some zone of certain thickness, say delta y, okay, in which molecular arrangement will be something like this. What is this? Here you can see that molecule of air is also present and molecule of water is also present, and mostly these are present in such a way so that their distances are in between this intermolecular distances here are very close. Okay, molecules are very close to each other. In this portion, intermolecular distances are large. So molecules are far apart from each other. But in the interfacial regions, the intermolecular distances will be in between the liquid and the gases. Is this point clear? So, in microscopic way, once we have this type of system existing, we will not be experiencing the sharp discontinuity in properties across the interface, but we will be having very smooth transition. Okay, so here density is equal to density of water, here density will be equal to density of air, and this particular band across which there is smooth transition in the property, that particular band we can call as our interface. Is this one clear? So it means that once we are looking at the interface from macroscopic viewpoint, it will be appearing to us like a 2D surface, okay, where there is sharp discontinuity in the properties. On contrary, if I look it from the microscopic viewpoint, in this interface between the two bulk phases, while property will be changing across the interface, it will be in a smooth and continuous manner. Okay. So because of which, why? Because of the arrangement of the molecules. And in this way, we will be finding that interface will be nothing but a three-dimensional water. Okay. Because along with this particular area, it is also having some thickness. So which is becoming a three-dimensional volume. Is this point clear? All are clear with this point? Now, any question? So this microscopic viewpoint will be very important for us to later understand the concept of surface tension. Okay, so from where surface tension comes into picture, that basically comes from the concept of microscopic viewpoint. Okay, so one important point let me discuss. When two molecules are very close to each other and when these are far apart, what happens? We know that when two molecules are far apart from each other, in that case, the intermolecular forces between them will be of attractive nature, attractive forces, okay. And when two molecules are extremely close to each other, okay, in that case what will be happening? These molecules will try to repel each other. So here the forces will be of repulsive nature, okay, and this particular nature of the forces is explained with the help of some potential. Say phi is my potential function and r is the intermolecular distance. When intermolecular distance is very large, then value of this potential is very small, and when the distance keeps on decreasing, the value of the potential keeps on increasing. Then it reaches a peak, and after that it starts decreasing and then become strongly negative. So in this zone, forces are of attractive nature, and in this particular zone, forces are of repulsive nature. Okay. So one important point is repulsive forces comes into play when intermolecular distances are very small. So that is the reason these repulsive forces are called as short range forces, because these comes only into picture when intermolecular distances are very small, whereas the attractive forces comes into picture when intermolecular distances are sufficiently large. So these type of forces are called as long range forces. Is this point clear? One is short range force and other is actually long range type of forces. Now it is important to know, if you have vapor molecules, and these vapor molecules, if we have to bring close to each other, it means we have to convert this vapor to liquid. What we need to do? So here molecules were at large distance, here molecules are coming close to each other. Okay. So already there are some attraction forces between the molecules, but we have to increase the magnitude of these attraction forces so that molecules can come more close to each other. Then only my vapor phase will be converting into liquid phase. So here I am talking about, say, water. So these were my water molecules in the vapor phase and these are the water molecules in the liquid phase. Okay. So we know that when molecules are actually at some larger distance between each other, then there are attraction forces. Okay, so they are trying to come closer to each other, but their energies, if their energy state is high, they cannot come more close to each other because they will keep on vibrating randomly. Okay, so in a situation of vapor, molecules typically have high energies, and if we have to bring them close enough to each other to form a liquid state, we have to remove some energy. Once we are removing that energy, then molecules can come close to. Okay, so we see that when we are having vapor, if vapor we have to convert into liquid, we have to remove heat from the vapor equal to that of latent heat of vaporization. So this much heat we have to remove from the vapor, then only it will be coming into liquid. Okay. On contrary, if I have to do the reverse way, say I am having liquid water molecules, but I have to convert these into vapor. What will be happening? Typically liquid molecules are close enough to each other. So once these are close enough to each other, these are having good attraction forces. Okay, so we have to break their attraction forces. So in order to break their attraction forces, we have to supply energy, and that energy what we are supplying will be equal to their latent heat of vaporization. Is this one clear? Now, third important point. I mentioned you that we have two type of forces. One are short range and one are long range forces, repulsive and attractive. Can you tell me what are the sources of these forces? From where these forces are coming and why these forces are coming in between the molecules?
To get charges, sorry.
Yes. So there are three things. One is electrostatic charges. Second effect is called as inductive effect, and third effect is called as dispersive effect. Okay, so there are certain molecules in which always there is existence of a permanent dipole. Okay, for example, if you talk about CO2, in case of CO2 what happens? Oxygen is more electronegative. It will try to pull the electron pair towards this. So it will be getting a permanent negative charge. And carbon will be getting a permanent positive charge. So because of which there will be existence of some dipole. Similarly, water molecule. In water molecule what happens? Again oxygen takes the electron pair towards its side. So delta negative is on oxygen, and this is getting positive. Which one? Yes. So because of which there will be existence of a permanent dipole, because of which it will be forming some hydrogen bond. Okay. Other than that, there are certain liquid metals in which there is formation of the metallic bonds. Okay. So because of their metallic bonds, there will be existence of permanent charges. There are certain molecules in which they do not have any effect, but whenever they come in closer with the, whenever they come in contact with the some other molecule, then because of their orientation, some another electronegative element try to pull their charges. So that comes under the category of dispersion effect. Okay, and in case of dispersion effect, always the nature of the forces will be attractive. In electrostatic and inductive effects, the nature of forces can be either attractive or repulsive because of their orientations and the distances between them, but particularly because dispersion effect will try to align the molecules in such a way so that one electronegative is actually trying to attract the other electropositive. Okay, so always in dispersive effect we will be finding the attraction forces. Okay, so with this basic understanding we will close for today, and we will discuss further in the next class.